The material is steel with a density of 7,872 kilograms per meter cubed. It has a Young's modulus of 200 gigapascals and a Poisson's ratio of 0.29. Now when you use beam elements in Abaqus, it's not enough to just define the start and end nodes. You also need to define the cross-sectional profile. So double-click on the profile item in the model tree. You see the Create Profile window. We're going to name our profile Frame Profile, and we're going to choose I as the shape, since our beams are going to be I-beams. When you click Continue, Abaqus shows you the Edit Profile window. Here we can enter in the exact dimensions of the I-beam profile. Type in the cross-section profile dimensions of the beams that make up the frames. Now we're going to create the profiles for the cross-brace beam members. We're going to name this profile Cross Profile. Now it's time to create sections. We're going to create two sections, one for the frames and one for the cross bracing. We're going to call the section for the frame section. We'll set the category to beam and the type to beam as well. You see the Edit Beam Section window. When creating a beam section, Abaqus asks you whether to perform the section integration during the analysis or before it. If you choose during analysis, you request Abaqus to calculate or integrate the section engineering properties or the cross-sectional behavior from section integration points during the analysis. This basically means that the section properties must be recomputed as the beam deforms over the course of the analysis. And this includes properties such as cross-sectional area, moments of inertia, and so on. The material behavior is also calculated at each point on the section during the analysis as the beam is deforming. This works for linear behavior and also for nonlinear conditions where the nonlinearity is a result of material nonlinearity. On the other hand, if you were to choose before analysis, the cross-section properties would be pre-computed at the beginning of the analysis. And then you would need to provide section properties such as Young's modulus and shear modulus and section Poisson's ratio. And that would be useful for a linear analysis or for a nonlinear analysis where the nonlinearity is also caused by other factors other than the material nonlinearity. So we're going to go with during analysis. You'll also notice that Abaqus expects you to give it a profile for a beam section. For the frame section, we're going to select the frame profile that we just created. We'll leave everything else set to the defaults and click OK. We can repeat the procedure to create the section for the cross bracing. Now that we've created the sections, the next step is to assign these to the parts themselves. I should point out at this stage that beam sections, such as the ones we just created, can only be assigned to wire regions. Now that works for us because the parts we created were made using wire features. If you recall, we used the create wire planar and the create wire point-to-point tools when creating the frame and when creating the cross bracing. We're going to expand out the cross bracing part and double click on section assignments. We select all the cross brace elements and assign to them the section we called cross section. Repeat the procedure for the frame part. Another very important thing I should mention when dealing with beam sections is that beam sections must be assigned orientations. Basically, Abaqus needs to know which way the eye profile of our beam is oriented. So for example, it could be on its side, in which case it would look like an H. So we need to orient it so that it is an eye. And in fact, the two flanges of our I-beam are not the same dimensions. So we need to let Abaqus know if the shorter flange is on the top or the longer one, and so on. And in our case, we want the shorter flange on the top and the longer one at the bottom. The shorter one was 0.08 meters and the longer one was 0.11 meters, if you recall. So let's go ahead and assign beam section orientations. I'm going to start with the cross bracing. So we want to display the cross bracing on the viewport. You can do this by double clicking cross bracing in the model tree as you've done many times before, or you could set the module to property using the dropdown, the model to beam frame, and the part to cross bracing, and that'll display the cross bracing in your viewport. Go to the Assign menu and choose Beam Section Orientation. Abaqus prompts you to select the regions to be assigned the beam section orientation. So we're going to select all the members of the cross bracing, as all their profiles are oriented in the same manner. Abaqus then asks us to enter an approximate N1 direction. The N1 direction is the direction in which the y-axis or the x-axis of the profile should be pointing. And the tangent vectors displayed in the viewport in red are basically going to be normal to the cross-section profile. Also, the cross-section is going to be sort of extruded out in the direction of those arrows. So in our case, if the normals to the cross-section profile are pointing out from the screen toward us, we would like the x-axis or the y-axis of the profile to be pointing toward the right. Therefore, we're going to enter in 1 as the x-coordinate and 0 as the y and z coordinates for the N1 direction. Hit enter on your keyboard, and you see Abaqus draws the orientations in the viewport. You need to click OK to confirm the input. Just to make sure we've got them oriented correctly, we can tell Abaqus to show us the beam profiles in the viewport. We use the View menu and click on Part Display Options. In the Parts Display Options window, check off Render Beam Profiles and click OK. You see Abaqus has rendered the beam profiles in the viewport, so we can see they're oriented just the way we'd like them to be, with the eye standing upright in the vertical direction, and the shorter flange on the top and the longer one below. Now let's assign beam section orientations to the frame. Switch to the frame part by choosing Frame from the Part dropdown. Once again, choose Beam Section Orientation from the Assign menu, and select the entire frame when prompted to do so. This time we're going to tell Abaqus that the y-axis or the x-axis of our profile points outward along the z-axis toward us. And click OK to confirm the input. You probably noticed that the arrows at the top and bottom of the frame did not point in the same direction. So this means our I-beam profiles are flipped on the top and the bottom. So we've got an upside down eye for the bottom one. Now I went with this just to make this tutorial a little easier, but if you'd wanted the beams to be the same orientation on the top and bottom of the frame, you would have to select the beam elements on the top and bottom separately when assigning the beam profiles, whereas we just selected the entire frame at one time and assigned a common N1 for the entire thing. We can then turn off beam profile rendering by going to part display options in the view menu and unchecking the option. Now let's create the assembly. We can instance both the frame and the cross bracing as dependent instance types, which means that we'll later create the mesh on the parts themselves. Now if you want to render the beam profiles in the assembly module, you once again go to the view menu and you notice that part display options has been changed to assembly display options. So click on that. Check render beam profiles and click apply. We're going to uncheck the option and click apply again to remove beam profile rendering. Now that we've got the frame and the cross bracing assembled, we need to specify what kind of joints exist between the cross brace members and the frames. But before that, let's talk about the joints in the frames themselves. When we created trusses in the truss tutorials, the nodes of the trusses were pin joints by default, because when you use truss elements in Abaqus, the nodes of the trusses are automatically treated as pin joints by Abaqus. Beam elements, on the other hand, are different, and the nodes between the beams are treated as welds. In a weld, the nodes are basically fused together, so you're going to see transfer of both displacements as well as moments, whereas in a pin joint, there's going to be no transfer of moments. Now we would like the joints between the cross bracing and the frame to be pin joints. That means they can transfer displacement, but not moments. We're going to explore two methods of doing this. The first one involves using connectors, more specifically joint connectors, and the second one involves using constraints, or equation constraints. We'll use connectors for the majority of the joints, and we'll use constraint equations for the rest of them. Let's switch to the interaction module by using the module drop-down menu. What we're going to do is create wire features connecting the cross brace to the frame at each of the joints. And we're going to assign all of these wires to a set. Then we're going to create a connector section and assign it to the set of wires using the connector assignments item. Let me demonstrate. Click on the Create Wire Feature tool. Now this gives you a window similar to the one you saw using the Create Wire Point-to-Point tool when you created the cross bracing. Once again, we're going to choose Disjoint Wires, and then we'll click the Add button to actually add the wires. Below the viewport, Abaqus prompts you to select the first point, so click on the first node. It then asks you to select the second point. Now needless to say, our nodes are going to be one above the other, since the cross brace meets the frame at that node. So we've got one node on the cross member and one node on the frame. And it's a little hard to see both the nodes. In fact, it's practically impossible to see them. But you don't need to worry about that because the second time you click on it, it's going to choose the node that wasn't selected the first time. We'll repeat the procedure for all the nodes, except the ones that we're going to do using the constraint equations. Click the Done button. You see that Abaqus has created a table with point 1 and 2 for each of the wires. Make sure you check off the option Create Set of Wires. This will make it easier for us to assign a connector section to these wires. You notice that Abaqus has created a set of these wires in the Sets item and has given it its own name, which is Wire1 Set 1. I'm going to rename this, so right-click on it and choose Rename. We'll change the name to Set of Connector Wires. Now let's create the connector sections. Double-click Connector Sections in the model tree. You see the Create Connector Section window. Let's name our connector Frame Cross Connector Section. Now you see a few different connection categories. There's Assembled Complex, which will give you a few predefined connection types, such as a hinge or a weld. Then there's Basic, which allows you to specify things like rotation and translation, and that's the one we're going to be using. And the third one is MPC, which is multi-point constraint. And these allow you to have constraints between different degrees of freedom of the model. And they can be nonlinear. For example, an MPC of type beam for 2 nodes would basically constrain the displacement and rotation of the nodes as if there was a rigid beam between them. And you can also use user subroutine MPCs if you went with that option. We're going to go with Basic. We'll set the translation type to join. This means that displacements will be transferred between the frame and the cross-bracing. So if the cross-bracing gets displaced a little way, the frame will also get displaced at the node and remain connected to it. On the other hand, we'll set the rotational type to none, so that the cross-bracing can rotate freely without affecting the frame, so there's no transfer of moments. Abaqus shows you the available CORM, where CORM is components of relative motion, as well as the constrained ones. So what it's telling us is that we've now constrained U1, U2, and U3. And that, as you know, is a pin joint. And you can click the Show button for a visual representation of this if you like. Then click Continue. We get the Edit Connector section window. We're going to leave everything here at the defaults.